Hi everyone, my name is Niar Ibrahim Rose. I'm part of SEA-ARMi, Southeast Asia Antifungal Resistance Monitoring Initiative, and I'm a microbiology researcher. And today, I'll talk about metagenomics post-processing, data visualization, and analysis, which is previously my colleague Vikran. He presented about the metagenomics pre-processing, and today I'll continue his work. So before I started, I'll a bit inform you what is the metagenomic post-processing. So mostly for the metagenomic post-processing, we will do the data analysis, which is we will visualize them and then do the statistical analysis and also integrate the data with good interpretation so that uh, can be used for the publication. So the outline of the metagenomic post-processing. So for the first, I'll introduce you about our program, and then the second about pipeline overview, and third about visualization script. So what is R program? So R is the programming language. It's widely used for data analysis and visualization, and also statistical interpretation. For the R, also it's free, and you can download it from their website here. But before you use the R Studio, you need to install the R first, because this is the basic language for installing the R Studio. And here also I give you the tutorial of the basic R, especially for in ecological usage, because in this training, online training, I'm not gonna inform you a lot about how to use R. So then how to download, as I mentioned before, so you need to install R first and then install the R Studio, which is these two different things. And then about R program, so you will see when you install the R and then you open the R Studio, you will see four panel. So for uh, the left the left up the left upside part is the source or editor panel, and then for the right side, uh, the up right side is the environment or history panel, and then for the bottom part of the right side is for the panel about files, plots, package, help, and viewer, and the left side, the bottom left side is the console panel. So for search panel, it used for you write the script, and then for the console panel, mostly it will show the R command and executed and results will be appear in this part. And then for the environment or history panel, is about shows loaded object, variables, and command history. And for the files, plot, packages, help, viewer panel is multi-purpose panel for file browsing. So in the R Studio, you can make your own project. So in this ribbon, but the second ribbon, you can choose the R plus here, and then you can make your own project in the new directory or existing directory or the version control. And then for the about the console that we use for this this training, we use R Markdown. So we click this plus the first ribbon, and then you click the R Markdown. And there is a difference between the R Markdown and R script. If you choose R script, you will it will the console it will show the uh the desktop the small desktop, which is only number and without any view of uh, the result later. And if you choose R Markdown, it will show more simple and it's easy to visualize the result directly for using the R Markdown. And the next part is the pipeline overview, which is my friend Vikran previously he already did for uh, the antifungal resistance processing and also taxonomy classification processing, which is from the Kraken 2 and also Diamond, we obtain the TXT files. So from those TXT files, we use that to visualize in RStudio program to visualize the pathogenic and antifungal resistance gene validation using NCPI or UniProt. And then for the specific to target WHO-APPL, to know about the fungal distribution and also fungal diversity. So for this training, I'll show you how to visualize the antifungal resistant gene bar plot in bar graph and heat map, and also for the fungal distribution using bar graph. So before we start for the script, so scripting in the R, so I inform you, so you need to curate your data. So here, I show you about the raw meta sequence data, which is the data after processed by HPCC. You will get like a long name. So you need to change the name with simple name. Sorry, the sample name. So the sample name must be same with uh, the data in the metadata, and make sure also for the format file, it must be in the TXT or CSV format, and make sure every file it's in the one directory. So in this training, I put all of the data in the one folder in the path in download. So I put everything here in the training data folder, and then I have the folder for the antifungal resistance and also for the taxonomy classification. So this is the first data that we obtained from HPCC. So we need to change it. Right? So we need to change the name. Change the name following the training mapping file here. So make it more easy to show. For the txt file, I recommend you to open in the Excel because it's more easy to control and to write. So here, as I mentioned before about the metadata is the mapping file. So the sample sequence here, the uh, the raw sequence that data that you obtain from HPCC processing, it will show long name like this. So you need to change the this name to the sample ID here. So beside of the data processing from HPCC, you need to make also the mapping file, which is it contain about the environment, about uh, the sample name, and also the sample information, the sampling information like the latitude, longitude, and then the province, because if you want to visualize later, integrate your data into the mapping, into the for example, like GIS data, like you want to connect your data into the uh, Google Maps, so it's more easy to visualize later. Okay, so now we start for scripting in the R Studio. So as I mentioned before, so for the source panel, we use the R Markdown here, as shown here, and also the sorry, the right side here is the environment panel. So before we start the scripting, we need to uh, install and also loading the package. So for example, here we use tidyr, tidyverse, stringr, readr, and dplayer as the package for processing the first script. So because I already installed, so I just load it for the package, and then for uh, the first line, so the step one, we need to do the data preparation. So make sure all of the txt file of the Kraken result into one folder, and then adjust the folder and pattern to your files in txt files. So because I already done in the one directory, and also already make sure all of the name files in txt files. So I just run it, and here, as I mentioned, in the environment panel, it show all of the data processing of the script. Then continue for the third script. So for the so for the second command line here, it's used for opening the txt file, and then for the third here, the third line, the command line we use to extracting the data. So they already extract here in sample underscore IDs here, and then we continue to the fourth command line. So here it show the function of the read Kraken report. So we read all of the percentage, read inflate, read direct, rank code, NCPI text ID, and also taxon. And then we count to make it to become a data frame here. So here need so far that you need to know is in the environment it show about the data frame of our data already processed so far, and then the value that we use to processing to get the data, and then the function that use also. So how it looks like for the data frame. So we can open here in this button, and it will show the percentage, risk direct, rank code, and CPA text ID, and then the sample ID. If this is for the important one, and the value here it show of the reads number of the taxon. So if you want to check like in the RQ1 sample, for example, like the highest, so you can sorry, for the lowest you can click first time, and click for the second time is for the highest rate, like here, but it showed unclassified. Okay, then we continue for counting the result here, and it show it show the data, but we will use it for the data frame to make the CSV file. So here for the the last step in the first the sorry in the last command line in the first step is we write the CSV file. So here we will make the HPCC training CSV, which is this data. It's containing the data of taxonomy classification. And then we continue to the step second. So we combine the CSV file that we obtained before with the mapping file. So this for loading the mapping file. So the mapping file, as I mentioned before, it's showing the environment sampling condition and also the sampling position, sampling location, anything you can add over there. And then we merge the data with the mapping file, and then we check it. So it's or just make sure if it's already. So here, or you can open in the merge data frame here. So here, that's what we get. So we already combined the rubber tree A, and then we have the fungal name here, actinomycetes, artoniomycetes. Unfortunately, for the HPCC, the metagenomic data, we just getting the taxon, not in the specific. Sorry, it's really different with the phyloseq data. So yeah, here we just can control from the rank code, and also we need to know about the specific taxon name. Okay, then we save the metadata, which is the metadata is containing the mapping file and also the taxonomy classification data. So we write CSV, and because I already have, so here I already have the training data here, the training mapping file, and also uh, the training metadata and HPCC training here, the new. Okay, so we continue to the second script about the metagenomic sequencing fungal WHO taxonomy PowerPoint. So I open the script here, and before you continue to the next script, you need to erase clear all object from the previous script, so make it not affect to the next script. So here we load some package, which is we still use the fuel package like dplyr, tidyr, string r, with r, and reshape. But here we need to because if you previously not install the new package like ggplot2, ggtext, scales, color space, you need to install. So how to install it? You just use this script or this. So you just run it. For example, like color space. Oh, sorry. So okay, so we can just, for example, like this one, we just install the ggtext. Okay, so here in the console panel, it shows the processing. and then it's already done, successfully unpicked. So that means you already installed for the package, and then just load it. And here in the console, it's showing. And if you don't want to use the script anymore, because you already installed, so you can just put hashtag here. So make sure the R not processing this one. Okay, we continue. We need to load the uh, load the package. Sorry, load the file. We use the training metadata. We load training metadata first, and then we check for the metadata. And then also this uh this script, the metadata, this first and the second here, it's for to select the sample data and make it and call it to remove the duplicate row, the duplicate row. So make the row and also the column in the metadata still in the unique SAM combination. And then the step two, we merge the and select only the FPPL. So we read the HPCC training CSV, which is the taxonomy data. We load first and then we count. And we replace the the sum of names that has a special symbol. For example, uh, for example, like this one, Candida aurita, Candida aurea, Candida bentonensis. It has the bracket, which is we don't want it. So that's why we need to use this script. So because we still so we need to check in cons meta data frame. We check Candida. So the bracket already uh, what is that name? Candida away. Example here. See here. So this is in the taxalong data frame, and this is in the cons meta data frame. So it's remove the bracket. Okay, continue. So for the next part is selecting the WHOPL, which is we have 96 name here of the WHOPL, which is we have some specific species or just only genus like here in the Mucorales we just specify based on the genus like Mucor rhizopus. So that means any species of Mucor, any species of rhizopus, it will be select in our data letter. Okay, we just started. Then as I mentioned before, so it's also erase filtering the data um, from the taxon of the cons meta. And then for the next step, for the command line 6, so we combine from the cons meta with the FPPL meta. Sorry, we combine the cons meta with the FPPL value. So we obtain the FPPL meta here. See, from 58,000, it becomes 3,000, which is it's showing we already select the genus and species that's in the uh our interest in WHO FPPL. Here, it already have some of Mucorales, Candida tropicalis, Candida albicans, Fusarium, and so on. And we do for the next step is the 3.1 about visualization. So for 3.1 visualization, one is about the aggregate of the crop. So we want to uh, select just only genus and species of the FPPL meta, and then we summarize the total of the FPPL meta of the WHPL, and here we use the threshold 0.5% abundance. So that means for after the FPPL meta is count with the less than 0.5% abundance, it will be changed the name species. So here we get per crop data frame. So here, for species that has less than 0.5%, for example, like this genus, the species name it changed to become 0.5% abundance. And for the species that have high 0.5%, it still show the same species, like this one, Madurella fahalii, and then Fusarium staphylae, Fusarium sp, Paxuela sp. Okay, and if you want to use the another number of threshold, you can use like this one, 0.1 as the less than 1% abundance. And if you don't want threshold, you can use this script I already reserved here. So you just copy paste. Later I'll show you what is the difference. So let's continue first for 0.05% abundance threshold. And then we replace the missing names. So if there are some names of the species is still in a unknown, so it changed to unidentified species. And then for the command line number 5, we grouping and normalize the data, which is for the statistical calculation. And then we check for the less than 0.05% of abundance, how many species? So here we obtain 30 species of the WHOFPL of our interest. So what is the difference if we use the no threshold? So I'll show you. So we just copy and then paste the script from the last line, the last bracket, yeah, to this one. We just copy paste, and then we use the sorry, it should be here, thresholding. So we change already. So there is no threshold here. So we redo the script, and then we just continue, and we check. There are 300 of 373 of WHO SEA-ARMi, which is we don't want all of these data show in our visualization because it will be so crowded. So that's why we use the threshold. But okay, now I'll show you what is the difference. Oh, sorry, if you use this 373 of species, it will make you give you a lot of work if you want to visualize them because for the next step, for the next command line, you need to define of the custom color here, which is here you need to write by yourself to to give the color uh, more specific for each species, which is not really good for visualization, and also it gives you a lot of work later. So that's why we use the threshold here to make more specific and select or for our result. So I'll put back for the threshold here. So we just copy paste and then yeah, we already have the 0.5% threshold. And then we continue. Okay, we have Turkey now. So because I already script for the species color, so we just uh, continue it. If you if you want if you have your own data, so I suggest you to get the specific color and rewrite the species here by your own. Okay, then we visualize it. So here we got it, the result. So here we uh, download the result in the JPEG format. So here I already put the script. So later on, if you want to change like the width, the height of the figure, and then the resolution, you can change by your own. Like for here, I want to change to 600 resolution, which is it's already good for the visualization. There is no blur, and also you can change for the X label, Y label here, crop, the relative abundance here you can change by yourself, but you need to make sure for the X value, the Y value, and the fill value is still the same because here X we use as the crop, and then for uh, the Y is for the value of the sorry the relative abundance of for each species, and then the fill is the color of the species that we already make this one. No, sorry, for the fill is the species too that we already select from uh the crop data before. Okay, so we continue to download it. So here that means we already have the result. So I put in the result folder. So here is the result. So here we are. So this is for the aggregate. So that means aggregate here is the combination between the sample replication 1, 2, and 3. So later I'll show you if you want to visualize them uh, in the separation of each replication. But before that, I want to give you more information about the percentage data extraction here. So we can extract the value of the percentage of each species from this script. So we use this script and then we just write this CSV file. So here I already make the training aggregate percentage. So it will appear in the same folder with the script here. So okay, so now we do the 3.2 about the another visualization as I mentioned before about the showing the sample replication. So we show for each sample. So basically for the script for the first part it's the same, but here for the different we use sample ID at the first, and then we use this one per sample, and in per sample we need to data normalization also, and then we check. So here it shows 24 genus with 0.5%, sorry, 24 WHO with 0.5% of the threshold. And why it show different? Because it's showing per sample, which is per replication. And the previous visualization, we did the aggregation, which is we combine all of the replication. And we continue to make the species that un- unidentified species, and then we customize the color. Oh, and also for this part, uh, I add about the priority group mapping. So here, with uh, the the genus and our sorry, with the genus and species of WHO VPL interest. So I put all of each species with the specific of priority group. Here, for example, Ixophiala aquamarina is part of Eumycetoma, which is the high priority group, and Fusarium is part of Fusarium spp group, which is the high, and because there is some unidentified species, or the less than 0.5% abundance also here, I uh, group them as unidentified priority. So, yeah, and then we uh, calculate data normalization. And then this showing for the unique, which is it's showing that the 0.5% is quite high. And then we reorder for uh, the priority based on the critical, high, and unidentified. Oh, sorry, critical and medium and unidentified. Medium and identified here. Okay, and then we define the overlapping species with this script and build the color, and then we check for the column names of the per sample average here or in the data frame. So here, unidentified species, and then there's the high priority, and because from our data here, just only high WHO. So yeah, we visualize them now, and here we get it. So okay, it's a big, but it's okay. So I put it like 1,200 resolution. because it's quite big for the file bigger. So what is so if you use 1200, so it show more bigger file size, like here 4 MB. So this is the result here. So it show all of the species with the high priority, the priority group, and you can extract the percentage also. Then we think it here. So you can multiply by 100. Oh, sorry. So because this is per sample, so you cannot drag all, because if you drag all, so that will mess for the sum. Here, so unclassified apomyces is the highest one here. So if you want to drag on for all, do this, and then make sure you know top uh, the top of the sample. Here RQ2, and then the bottom part is here. So we get 100. So yeah, and so on. So this is for the first visualization. Sorry, the first visualization of the taxonomy bar plot. So we continue for the next visualization for fungal AMR data. Okay. So here, as I mentioned before, we need to load the data. Sorry, we need to load the package first. Okay, after that, so we need to load the file. So for the first file that we need to load is the fungal AMR data that we obtain from diamond process, which is the fungal antifungal resistance gene data. So because for that files is in CSV format, so we need to change for the files list name here. Previously we used txt, and then here we need to change in CSV. So we upload it because I already done, and then we define the column. That the column in the data that we obtain. So we expect the column here, and then we read the data from the folder, and here we got the data frame, the MM6 all here. So these all are our data. But it's really hard to read because the title here is quite long, and then for the sequence ID, it's quite long also and not easy to retrieve. So we need to curate the data first. So we check the data frame. Okay, and then names, it's already same with our expected column. We have 15 plus 1 about the sample ID. And then because we have in the MM6 sorry, MM6 all data frame in the S title, which is our interest column. So in the S title, we have long name of the species, about species here, and then also have the protein, also the gene. So we need to retrieve all the information from this column. So how we retrieve it? So we use this script. So in MM6, it's already changed. Sorry, we already obtained the species here. That previously we don't get it, but now we have it. And then we continue to, oh, because from the MM6 here, there are some of the species with long name here, like this one, Cryptococcus kti with OX something, and this on, which is we don't want to have this name in our data letter, so we need to use this script to select all of those names. So we run this script, and then we check again, Cryptococcus kti, it's already clean, I think. Um, oh, yeah, already. So which is good. And then or we can just like check here. So there is no, okay, so we can continue. So we also can retrieve the genus name from the species table with this script. So we can check, and the same data frame, we obtain the genus here. Okay, we continue to filter. Okay, so for this part, we want to uh, select the percent identity of our gene result, the antifungal resistant gene with the highest than 70% with higher more with more than 70%. So which is PIDEN here. It's quite diverse. There are 31, 27, and the lowest is 19.6, and the highest is 95.6. And we just only have here, from here, we have 70. So these data that we want to use to continue for the next part, because we just uh, make sure the percent identity with more than 70%. If we use the threshold with more than 90%, so that means we just only have these two data. So we select, identity, 70%, which is it's also optional. It depends on your interest. If you want just only 50%, you can go also. And then we continue to the data alignment with the UniProt database because for this antifungal resistance gene data that we use based on the protein, so that's why we use the UniProt database. But before that, we need to filter of the accession number from the S6 ID column in the MM6 filter. So what is it? So here we have the number of the uniprot here, which is in the middle of the long name here, which we need to retrieve it with this script, and then we just print it and we have it. So we use this name, sorry. So for the next command line, we retrieve the gene information from UniProt database. We already have 15 accession number here, so we just use the unique MM6 accession, and then we just run this script. We retrieve directly from the UniProt database. So this is the function, and then we go for another function, and then we extract the expression. And after that, we after the extraction of the accession number, we align the UniProt information. So here we have the accession, we have the gene, we have the protein, we have the organism also. So we can use this information for merge, and we get it. So we have MM6 annotated. So here it's quite clean. We have the specific information which already have with our sample ID, species, genus, accession, gene, protein, and also the organism. But the organism we can use here, the species and genus. So it doesn't matter for this organism information. And we continue. So for the gene that showing an A name, no, here in A gene. So we change it with we substitute the name with the putative gene because uh it has the protein information, so it belongs to cytochrome B, so we can change to a putative gene here. So here we get putative gene information. And then the step 3 is the data analysis. We need to calculate the antifungal resistant gene. So here we get the data calculation. Hits number 2112. And then continue. Oh, and in this script, because during this process we have issue about the database that we have with not specific WH4PPL, so we need to eliminate it. So there are alternaria species here, which is not our interest in WH4PPL. So we can use this script to filter, and then we check it again, TNR count. So here, there is no alternaria anymore. And then we combine with the mapping file. So we load the mapping file and then we merge the AMR counts data frame with the map data frame. It becomes AMR by group data frame. So what we have here, we have the crop information, we have the gene, species, protein, and total hits number. And then now the step 4.5, 4.1, the data visualization. So for the first part, we make the aggregation bar graph. So we use the X as the crop. So it will show just only specific gene with the crop without replication because this already aggregate. We already summarized all of the replication. And then we save it. And we can visualize them in the heat map. If it's showing something like this, but it still show our uh, visualization and there is no error information, so that's still okay. We can still use it. And then we retrieve it, the figure, and we see. This is for the heat map. And then this is for the bar plot. It's quite big, which is we can adjust it for the font size, the species, the legend size, legend font. Okay, so that is for the aggregate, and now is for sorry. Now for the data visualization per sample, which is per replication. So we use the sample ID instead of crop. Okay, we calculate already. We use the sample ID as the vector, but it will show here. RK2, Aspergillus, and yeah, and our base sample, and then here the visualization. This is for the heat map visualization. So it show one which is so less for the this gene, but here the two the hits two, so it means has a bit higher than the hits one here. We can adjust for the color. So that's all for the visualization. So I'll give you the recap of the summary of the pipeline. So for the first that already done by my friend Vikram. So the route sequence here from the FASTQ uh, GZ, we process it with Boity to decontaminate the sequence and then assemble the sequence by using megahit and assembly analysis by BOSS. Then we use Diamond to uh, predict the antifungal resistant gene, and then Kraken2 for the taxonomy classification using the fungal 5K database, and we use RStudio to visualize the antifungal resistant gene in bar graph and heat map, and also specify to target WH1VPL from the Kraken data with the bar graph. So hopefully, this this result can help you guys for visualization for your data in the future. So we already write everything here in our website. So later you can check here in our website. And thank you everyone.